the positive, right? Positive down.
Oh yeah, negative would be.
Yeah, positive down, negative up. Yep. Okay. And also, I keep saying this is the answer. I don't know if this is really the answer. I think, is it the answer? It is the answer. Okay, this is the answer. You can compare your results to this. But then this is the envelope, right? This is what you're making in part one, right? And that envelope is independent of your tendon, right? It's telling you where your tendons are going, right? And so you don't need where the tendon is at the beginning. You don't need to know where where that EP is. I came back and I plotted later that this is its location for one of the far, the later on problems is what plotted there. But really your answer is that without the black right there. I set mine up so that it's like the dashed are lines you need to stay below and the solids are lines you have to stay above, right? And the ones you have to stay above are controlled by the initial conditions, and the ones you have to stay below are controlled by the and then this is what I'm talking about, how, right, if you increase your initial tension stresses, these guys go down, which means you can move your tendon profile down in that case, which means the amount of load you can put on there goes up, is what I'm looking for in that. But obviously put a little more thought to it. And then these are the stresses that you get for the different cases. And I just keep them separate. And that's pretty straightforward. Any questions about it? Yeah.
To calculate the stresses, you approximate EP as a
parabola. Yeah, that's right. I estimated it as a parabola. Yep. And so that was I just fit a quadratic equation to those endpoints or whatever, and you get it. Yeah.
So what's the thought process for like which one you have to stay above? Like since you have to stay above the initial conditions, and
Yep.
stay below the surface.
So what's happening with that, right, is under initial conditions, right, it's a pop-up versus a squish down. And so without any loads on it, right, with just the self-weight alone, and they cut those tendons, and, right, or if they post-tension it at that point, what's going to happen is that things are going to pop up, right? And you want to minimize your pop-up, right? And so that means you have to stay above that. You got to stay above it, because the further you go down, the more pop-up you get, right? And so that's why the initial conditions, right? The initial conditions are the ones saying stay above this value, because if you go below it, you get too much pop-up and you can run into compression at the bottom. In this case, it's tension that's controlling. You get tension up at the top that can control it. So that's that. Under the loads, now you're pushing the thing down, it's bending down, and then in that case, you want to put your tendon as low as possible. If it goes too high, then you're not getting the full benefit. You're not getting enough negative moment to cancel out those positive moments. And so that's why it's saying, you got to stay above that value.
Okay, thanks.
Okay. Yep. Yeah.
Do you want us to send you our Excel spreadsheet or just print off the graph?
I would have the Excel spreadsheet too, just in case something went wrong or whatever. So kind of document your spreadsheet, label your columns and stuff like that, make it nice and neat. But yeah, I give me both of those.
Do you want us to just email it to you?
Oh.
You're gonna have a Dropbox in like 2 hours.
This is Biles. I haven't thought about this yet, man. I don't need the Excel spreadsheet, just to print out. Just to print out of it. No, I mean, I'd like to see it, just to print out of it. I don't need to see, like, if you have every point one or something like that, I don't need to see, like, the pages of your output, but just maybe that front page, like just the top, and then you can cut it off at a certain point. You know what I'm saying? Like, if you made your X go 0.1, 0.2, 0.3, up to however, I don't need all the numbers the whole way, but just kind of a summary page of it would be good. Cool beans. I got this thing, it just happened the last few days. When I'm talking, I suck my mask into my mouth. And if you've done this, it sucks because it stops your breath immediately. Like, you can breathe through it when it's not against your mouth, but when you suck it into your mouth, it's jarring. And I don't know what's happening. My wife says it's because I'm a mouth breather, and it is true. But when I'm lecturing and I'm getting all excited, it's like, it stops you. Oh God, I think I'm gonna die a little bit. It's a terrifying experience. So Dude. Anyway, so I might have to. You might see me pause up here. It's because I've sucked my mask into my mouth. And then it gets wet. And you have your lecture. Your mouth is all wet. By the way, people are getting sick, so stay vigilant here, right? It's happening. Right? A couple people from this class are sick right now. It's just like, oh, not necessarily COVID. There's a bad cold going around as well. So, yeah, stay vigilant. It's happening. Things will take it off again. Okay. All right. Are we cool? You're working. I'm glad. It's great. You guys are working on your homeworks. Right? I'm assuming those without questions haven't started their homework. Is that correct, John? Right? Or, yes, Brandon.
On this last one, it looks like, well, the reds are on the top and then the reds on the bottom. Is it just?
Oh, did I just do that? I might have just done that.
Is it just?
Oh no, it's. Yeah, that's right. Because see, this F2 is the top. F1. Yeah, see, we got all sorts of stuff. F1 is the bottom. So bottom is compression issue, right? So this is compression issue, and then the top is going into tension, and it's approaching that limit. And it should be reversed, because under service loads now, instead of bending up, now it's bending down. And so in this case, now it's the compression at the top that's the problem, and then the tension at the bottom that's the problem. Yep. And those are fine. And so basically, if you violate it, like if this thing goes above that line, then it's a tension problem. If it dips below this line, then it's a compression problem. And then, same thing on the things up above there. Also, if you see a violation down here, like if I went through, so these are the stresses given that tendon profile that I have up there. If that tendon crosses one of those lines, then down here in these stress plots, you would see it also violate those things. They're really tied to each other. So I think so. If right in here, like this thing went above there, then down here I would see that same violation. It would violate the stresses down below, and so you should see that in your answers too if you're plotting them all at once. Okay. There's a lot going on in these plots, right? It starts out with P over A. Right, as I said at the beginning, it starts out as P over A, My over I, easy mechanics. But then there's all these load cases and stuff like that floating around, and things get crazy pretty quick, right? And then there's all these limits, the ACI prescribed limits at the initial conditions and full conditions, and then there's sustained load and all of that stuff. What's nice is all that stuff is captured by these simple plots, and as long as you don't violate those stresses, you're good to go. If for some reason violate it, change things about your design, and then these things update, and you go from there. Okay? All of this stuff, though, all service conditions, right? They all have to do with service conditions. But then we obviously care about more than just service conditions. We care about people dying, right? And so therefore, we have to worry about ultimate capacity, so we need to check our ultimate capacity. So you kind of design for service conditions. Oftentimes that designs most of our controls of your design. Right? There's a whole purpose. The whole purpose for doing pre-stressing is to prevent cracking and improve your deflections and stuff like that. If you don't want to do that, just do regular reinforced concrete, because that pre-stressing does not increase your capacity much. Right? It's not about that. It's all about service conditions. You pay a premium for it, but you're preventing these things from failing. So those bridges that we built, empty as you're part of this, the bridges we built in wisdom, right? Those are aiming for like 100-year design life, right? If they don't make it, I don't give a shit. As long as they make it like 50 years, then I'm in the clear, right? Because we're not even that. 50 years I'll be dead, right? So like maybe 30, 20.
I mean, you won't care.
Yeah, I won't care. I won't care in 20. Others are going to die in 20. I might die in 20.
They might come sue you.
My mid-60s. There was we talked about this summer, last summer. Kirsten thought it was funny to like send out an email telling me happy birthday because it was my birthday at work one day. And she said that I was 60. Right? Just as a joke. She said it was 60. It's freaking Elias believed him, right? So and I was like, am I really that old looking to think that it's actually possible for me to be 60? And I guess the answer is yes. Like he said, he was pretty amazed. He said, "You're in a." So he was debating with. I think you believed it too, didn't you?
did,
Yeah. MTS, I think you were in that boat too. Screw you guys, right? And they were like, is he in really good shape for a 60-year-old or bad shape for a 40-year-old? Like which one? It was this internal battle that was going on in between him. Bastards, it tell me 20 years. It could be. Who knows, right? Who knows? Okay, so we're calculating the ultimate capacity. Working our way through this. Same mechanics, right? Whitney stress block. C is equal to T. Solve for where the neutral axis is, right? It's just now it gets complicated because what do we use for that FPS? It's not just Fy, right? It's that if we assume it's Fy, it's not accurate, or it's not. It's not accurate. It's just an assumption. Whereas, it is more likely for that to be the case in regular reinforced concrete because they have a nice yield plateau in their steel. So what do we use for that FP? Well, it gets complicated, right? There's a couple different methods, right? We could just assume that it's Fy, or we could use this empirical relationship derived by, prescribed by ACI. So either you assume it's Fy, or you assume it's this, right? Very prescriptive method. You just go through and you define each of those variables, plug it in, now it pops an FPS. It's not an iterative process. You can directly solve for the area when you do it that way. And you go from there. The other, what we're in the middle of, right? The more accurate method for doing this is using strain compatibility, okay? And when we do that, there's all sorts of, it gets pretty convoluted, right? We use the same methodology. You set C equal to T, you solve for X, but X ends up being on the C part of the equation and on the T part of the equation, right? It ends up both of those. And what we were defining was, where are these strains? So there's three different, so we need this strain, we need this total strain to say where are we at on that stress strain curve. So I need to figure out what that is, what is the elastic strain to begin with, and then I add on to it what they call the decompression strain, and then on top of that is our what we call EPU, our ultimate strain, that's beyond the 0 point, and how much curvature is it showing before failure. So that's what we're kind of middle. Once we get that, once we know what that strain value is, you go into our stress strain curve, right? And then you plug in this strain, or this total strain, and then into this equation. That's the equation for the stress. And then, boop, tells you what your FPS is what it's gonna be. So we're gonna use this thing. So you're gonna have a homework where you calculate the ultimate capacity with all three of these methods: Fy, empirical equation, and strain compatibility, and compare it. Okay, we weren't done with this one yet. This is kind of defining what those three different strains are, right? And I won't beat the horse too much to death here, but this is it at initial, right? When you release it, the concrete kind of squishes back down. Everything's in compression at the bottom and the top, and that's epsilon to PE, right? And then we calculate that as just what is my pre-stressing stress divided by the elastic modulus. That tells me what epsilon to PE is. And so in your code or in your Excel spreadsheet or whatever it is, you'll have one of these things that says epsilon to PE is FPE over ES, period. And then you move on to the next part. Then it goes into epsilon to PD. I need to get this thing decompressed. This right here is what epsilon to PU is. We'll talk about that next, how we calculate that. But before we could do that, we have to calculate what that is, which is the decompression stress. This whole thing is about the decompression stress, right? And again, if I were you studying through this stuff, I'd kind of make sure you understand each of these steps, like where they came from. But really the key for your code is just this part right here that I have boxed in red. That's the key part of your code. So in your code, you would have one that says like epsilon to PD or EPD or whatever it is, and you just straight up calculate it. It's going to be your pre-stressing force divided by E times AC, that whole thing times 1 times epsilon to P squared divided by 1 over AC. So you just calculate it once. That doesn't change with the neutral axis location. That's just a boom, you just calculate that. So you calculate the first one, you calculate this one, but then the next one,
isn't EP a function of x possible?
here, this is where it's going to be a function of x. So the first two So you're right. The total one is from,
But I mean, your tendon location could be a function of X, right?
yes, right, yeah. So that's great. I was going to mention that later, but thank you for bringing it up right now. So this is for one location along the beam for what an EP is. This is changing as you move along the thing, right? Because if it's draped or if it's harped, that's changing. So really, technically, you'd have to do a FMN for every location along the length of the beam because EP is changing and your moment is changing, right? Usually it's going to be that middle, but maybe not so, because in the middle, your EP is the biggest, which means your FMN is the biggest. And so it's good, but then if you move away from it, then it goes out. In your homework, we're going to do it in one location. But you're right, that EP definitely changes as you go along. And in fact, John Lovegreen, when he was in this class, he works at DCI where Amanda works, he went through and he solved it at all locations. And it gets pretty dang close outside of that middle in a couple places because the EP is changing. So I see what you said, yep. So that you were talking about the actual EP. This, right, this EP, right? Right, and then that's also going to come into play later too when we look at those triangles, similar triangles. So this one, epsilon sub pu, this is going to be a function of a different x. So you've got two x's floating around that. There's the x, what we're defining the height to the neutral axis, and then there's also x, which is the length along the beam. I should probably call it c or something else to avoid that. But then there's the capital C, so in regular reinforced concrete. Yeah, you pick it up when I'm putting it down. Okay. So in this case, so this is the last strain we have to calculate. The other two we just calculate straight up and then we move on. This strain comes from this triangle. Straight line there. Right. This is fixed at 0.003. This is that neutral axis x. Right, which is equal to a over beta 1. Right, that comes into play a little bit later. It's related to what our Whitney stress block is related to our Whitney stress block. This distance here, from here down to our pre-stressing, we'll call that dp. All right, and based off similar triangles, we know that 0.003 is to x as epsilon sub pu is to dp minus x. All right, and that value right there is epsilon sub pu. All right, epsilon sub pu is this guy down here. That distance right there. And so you're comparing this triangle. Right? You should be used to this from regular concrete to that triangle. Right? They're similar triangles. And so that's all that this is saying this length to this length is the same as this length to this length. That's all that is doing. And so you can calculate what epsilon sub pu is. 0. Over x times x. And then, so then in summary right here, your epsilon sub ps, my full pre-stressing that goes into that constitutive relationship is equal to epsilon sub pe plus epsilon sub pd plus epsilon sub pu. And then as you can see, this is a function of neutral axis. We'll call it neutral axis x. Boy, I taught this class so many times, I've never noticed that we introduced a new x, right? I should notice that. Thank you, Matt, for doing that, right? There's an x this way, we're our neutral axis, but there's also x along the length. This is not the x along the length. This is the x in the neutral axis direction, right? So this is where our t is a function of x, it's hidden in this, right? Our t is a function of x, is our epsilon to pu is a function of x with that equation right there, right? So that t is a function of x. It's going to be, you're going to go to the constitutive relationship given this epsilon to pu. If you change the neutral axis, then epsilon to pu changes, which means that on our constitutive relationship it changes. And so that's changing on the right-hand side. On the left-hand side, c is changing as a function of x because our neutral axis depth is changing. And so it's a balance between. We want c equal to t, but it's on both sides. Okay, we'll put it all together right here. Kind of summarize it right here. Okay, so we're gonna do this. I'm gonna just say this is like a, hey, Sutton, could you hit that door? Okay, we kind of show this for like a rectangular section, right? It would work for a T-beam, like what I'm gonna show you here too, but just for a rectangular section, or at least where it could be a T-beam or an I-beam, but this would be a case where it stays, the compression stays up in the flange and it doesn't go down, because it gets a little more complicated when it dips down into the web. But if we keep everything up in the flange, it's gonna be this, okay? So this is just for the demonstration. It is the same process stands for, for other types of sections as well. So this is your equilibrium. C has to be equal to T. Otherwise, it's accelerating, it's rotating around and stuff like that. So this is 0.85 F prime C, A times B, right? The Whitney stress block multiplied by the area over which it acts, which is A times B for a rectangle, right? Again, I guess I could draw that here so you know what's happening. Oh my gosh. I guess we'll take it shaded. Right, this would be B. Oh. As a width of B. And so it's like, what area does it act over? That compression block. Right, this height right here is A. That's 0.85 F prime C, A times B. And that's equal to area of the pre-stressing multiplied by FPS, which is our stress in our pre-stressing strand. Right? We put this in terms of x, 0.85 F prime C times beta 1 times x, that's what A is, times B is equal to APS, FPS, which is a function of epsilon to PS. I'll make that a green, red color. This is where the constitutive relationship comes in. That's what I mean. It's a constitutive, it's a function. It's not FPS times epsilon to PS. I just mean function of. Okay. And then this epsilon to PS, to make it clear, that is a function of x. Neutral axis x. Okay. So on this side of the equation, it's a function of neutral axis x. And on the right-hand side of the equation, it's a function of neutral axis x. So there's a couple ways you can do this from this point, or one way you can do this is you can plot c as a function of x and t as a function of x, and then you have the two little curves that go by each other, and where they hit each other is the answer, like on where that neutral axis is. That's one way you could do it when you get into this. Side note, you plot both of those. That way works pretty well. And you're just like, man, you remember that back in the day, right? You plot two curves and then like where they cross is the answer. You would probably program that into your like TI-84 back in the day, right? You know what I'm talking about, right? And you're like, yeah, that's how to answer that thing. So that's one way you could do this. And then Excel do that. Okay, let's keep going with this. The right-hand side of this. This to try to make it clear. This is going to be APS actually, let's just do this. I'm gonna go like this. I'm gonna go like that. Epsilon sub PS is equal to epsilon sub P E plus epsilon sub PD plus epsilon sub PU. This epsilon sub PU, just to make it clear why it's a function of x or how it's a function of x, that's equal to that equation on the previous page, which is 0.003 divided by x times dp minus x. So you do is the easiest way to do this. Well, let's write this down. You'd say come on. I'm gonna shut this. I'm gonna type this here. C equals T and solve for X. Right. Okay, I mean that's really what we're doing. But it's kind of nonlinear. Like in reinforced concrete, you could just outright boom say this is equal to this. What's X, right? It was straightforward because there wasn't all this. It wasn't on both sides of the equation. Here, it ends up being an iterative process because it's on the left-hand side and the right-hand side, okay? So you could, so what you could do, I mean, like I said, the easiest way that I know implement in Excel. There's some commands in MATLAB to do this. There's like a command called F0 that you can make this work as well. There's an F0 command and there's some other stuff, but it involves a little bit more knowledge of MATLAB. But if you want to do it, you can do it either way. I think typically in this case, it's pretty straightforward to do it in Excel because you could use some of their iterative processes. And use goal seek to solve for X that makes this true. I think what I do is what I've done before is I set up a cell that's equal to C, and it's a function of this other cell over here, so it's equal to that. And then I set up another cell that's T, and it's a function of that same cell up here. They're both equal. They're both a function of that right there. And then I have another cell, and I say C minus T, and I do a goal seek to make that value equal to 0 by changing this value. And so you just say that once, and Excel goes, and then it does guess and check, and it works its way into like solving it. I think that's the best way to do it. Stanton in his notes lays out a process for solving this. I would not do it the way he lays it out. He does it like if you were to program a solution algorithm in like an iterative solution algorithm into it, he lays it out that way. So he lays it out, well, you go in and you guess an X, and then you go through and you see is your C bigger than your T. If your C is bigger than your T, move it this way. And then go through that. And then if your T is greater than he kind of like works you through like converging on the right answer. That's already built into Excel. That's built into the goal seek. That's what goal seek is doing. It's going in, it's like, if I change this, then what does it do? If I change it down here, what does it do? And then it just automatically kind of goes through and solves it for you. Okay. Same thing in Excel or in MATLAB, the command's F0, so you can set up something very similar. We have F0 of C minus T, and then it'll go through and guess a bunch of X's until but it involves a little more coding. What else? C is equal to C, solve for X, easy. You could also C and T as functions of X, functions X, neutral axis X, and find That also leads you to the right answer, okay? So that's not your answer, by the way. We're not done yet. See, that's trying to find out, you're setting C equal to T. That tells us where our neutral axis is. And then at that point, we have to calculate the moment, right? We haven't even calculated the moment right now. All of that was just trying to find where, a long ways back up there, right? Where this neutral axis was. Where is A? Like, where's our Whitney stress block? All that's about it. I mean, it's about implying equilibrium and then where that's at. So you got to come back to here. Once I know what T is, once I know what C is, once I know where C is located, then I calculate the moment, right? And it's just C or T, either one, C or T, because they're equal to each other, times the moment arm in between them, okay? Get on there. Once you know X, they'll give us A, and then M is equal to T times the moment arm, right? Or C, either one, because they're equal to each other. And so then you end up with Mn, in this case for a rectangular, same one before, T times D minus A over 2. dP, I guess, in this case. Right, that's for a rectangle, right? That's based off of this. Right. That's T. I guess we might as well put it here. That's dP. Right. A is that Whitney stress block that's like that. Right. And so this distance in between them, that right there, that's dP minus A over 2. That's just back to regular reinforced concrete. If you had a T-section and you had a flange and you had a web, there'd be two C's up there. There'd be a C for the flange and a C for the web. But you go back to the same thing. You sum the moments around a certain point. Everybody see where the A over 2 comes from? The A is the whole depth of the stress block, and then this is actually the middle of the stress block. And so, okay? Simple as that. Okay, what's nice is if you use one of those other methods, right? If you use one of the other methods, you just know what FP is. You go back up to this, like here, instead, right? You look right here, and instead of FPS being a function, actually you go even to right here. Instead of FPS being a function of the neutral axis X, it's just a value, right? When you use the F, if it's equal to Fy, you use the value, or if it's equal to the empirical equation, just gives you this. And so then right away you solve for the neutral axis. That's the only unknown in there is that neutral axis. You solve for that neutral axis, and then you carry on and calculate your moment like down below. Calculate your moment like this.
So how do we know which one to use?
Or I tell you, do all three. Yeah. So you're gonna do 3 and then make a comparison on like which one's better or which one's worse and stuff like that. Is one more conservative than the other? So. But again, once you get the code working, it's pretty easy just to change what that FPS is. We're like ahead. This is so rare for me to like be ahead of schedule, right? Because like you're doing a homework on this is like next week's homework that we're already talking about on Wednesday. Very rare for me. Any questions about that? Okay. The other thing, if it's unbonded, all that stuff up above is bonded, right? It's pretty academic, right? Like I said before, if you were in industry, you'd probably just use the ACI prescribed method. You'd say, yeah, here it is. This is what I use for that value. If it didn't work out or it was close, then you could sharpen your pencil and dive in a little bit and do your strain compatibility method and get. And once you see it, once you implement it, it's super easy. You can carry this on in the future if you want. And once you make that graph. And as an academic, we got to do this, right? Because it's way cooler when you got to iterate. We got a solution that we have to iterate, right? Amanda, this is cool stuff, right? 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 And so, yeah, thank you. And then that's why I went into academia, by the way. It's because I wanted that. I craved that, like, give me my MATLAB. Give me, right? You're enjoying the program stuff. You're programming in Python, right? Like, he's doing his own stuff, right? You guys don't even know what Python is? It is Python, right, that you're doing it? Yeah. It's free, right? So MATLAB costs money, and so if you go into industry, you don't have MATLAB at your disposal, but you do have Python. Do you use it in work? Sometimes you do?
I mean, not so much in the past in structural, but.
Oh, yeah. If you do, you keep it a secret from Jason and Tom, right? You're like, your boss is, oh no, I didn't program it. I don't know what you're talking about. I didn't open Python today. Okay. Unbonded postage. So all that stuff is for bonded. We've now moved on. All right, so so this idea of strain compatibility doesn't work, because now we're talking about a tendon that's loose inside of the concrete, and so there is not a strain compatibility. The strain in the concrete is not the same as the strain in the steel. When the concrete bends, the steel will stretch, right? But it's not localized right to the same thing that the concrete is. It's spread out over the whole length. So when you push it down, it will stretch it a little bit, but it stretches over the whole length as opposed to just at that location. And so you can't use strain compatibility, but obviously you still need to calculate the ultimate capacity. And the way they do it is with this right here. It's just a prescriptive method, similar to the other one. Similar to the prescriptive method for bonded pre-stressing, very straightforward. You just calculate it as according to this. Okay, so we could say that A does not apply to deboned. That doesn't work for deboned either. Debonded, unbonded, say unbonded, that's a better one. Not unbounded, unbonded. It's a word, trust me. Well, maybe don't trust me, but I think it's a word. Unbonded. Yeah. Thank you. Unattended. I'm trying to think of what else to say. Must use empirical prescribed by ACI, which is what you see over there on the right, because they're not attached to each other. I think Stan spends some time. Again, I gotta point out, if you haven't opened up Stan's notes, open up Stan's notes and just gotta read through it. Like he talks about all this stuff. I've just put a spin on it, my spin on it. You open it up, take a look at it. He does talk about this. He talks about how it's not bonded, it's distributed over the length. And people try to model it that way and stuff. So take a look at this stuff. Okay. Any questions about this stuff so far? So we got to go on to feed factors. What do we use as feed factors for these things, right? They are reinforced concrete beams, but they are different, right? They're pre-stressing. Turns out you use the same as for regular reinforced concrete, which are these guys right here. Right? It's this plot over here. Right. Typically, you don't find spirals in pretension members. You'll see stirrups and stuff like that, but in that case, right, you'd be on this curve right there from 0.65 hits this where you get initial yielding, and then it starts ramping up until you get into what they call a tension controlled member, and in there it's 0.9 from there on out. And so you get rewarded for having ductility, you get penalized for not having ductility, right? And if you remember, in regular reinforced concrete, there was a 0.004 limit. You could not. You remember that? There's a 0.004. You can't have less strain than 0.004. You always have to have at least 0.004. That limit goes away when you're doing pre-stressed members because you have all this compression. That compression's helping you. Like that 0.004 limit says, like, if there's no axial load. In this case, we have huge axial loads because we're pre-stressing everything. So you can actually go down, all the way down to 0.65 on your fee factor, okay? And so this is a function of your strain in your steel, right? This epsilon sub t, right? It's a function of how much, and what this is kind of a measure of curvature. The more epsilon sub t you get, the more you see your beam deflecting, right? Because the whole idea is this is to make sure that you have a ductile failure, that there's warning in your failures. So if you look up at a beam and a thing is sagging down, you get the hell out of there, right? You don't want this thing to have like no warning whatsoever and then come crashing down, right? Like if it's gonna fail, make it deflect first before it fails, right? And so you get rewarded if you make it deflect a bunch, and you get penalized if you don't let it deflect a bunch. So if we look back at our strain, so in regular reinforced concrete, there's only one strain. It's the epsilon, what we're calling epsilon sub PU. There's only that, right? In pre-stressed concrete, there's the initial pre-stressing strain, right? Elastic pre-stressing strain, there's the decompression strain, and there's the epsilon sub PU. So which one do we use to compare here? Like, what are your thoughts? PU. It's going to be the PU, is because that's the one that you would see. The other ones you don't see. The other ones are making it kind of like go like this and pop up and stuff. But if you want to see, we want to find how much is it bending down right before failure. The one that's bending, the one you're going to see is this one. This is the one it's bending down and it's going to be failure. So when you look at that limit, you're comparing what epsilon sub PU is. And so, that's easily stated right here. We just say, in this equation right here, we say epsilon sub t in that equation is equal to epsilon sub pu. All right, and that's epsilon sub pu. This is 0.003. Right, it's that one. This is the one you see. Is what you'd see before failure. Right, and you can imagine that those other strains, well, especially the epsilon sub PE, that one's all about it's a huge. First off, it's a big value. It in itself might be bigger than that 0.005. So it might not even be like failing at all. It might just be popped at just total pre-compression or pre-tension and pre-compression on the concrete is popping up, and you're already, even as though it's not even deflected down at all, you're already at the 0.005 because it's already pre-tensioned. So that one doesn't really make sense. It's the one that happens after all that other stuff and right before failure. So it's that epsilon sub PU. These are one of those things like in the code, like they don't tell you that. This is what I say. The code's really good about like if it's, and I had a conversation with several of you. If it's something like you don't really know, or this could be open to interpretation, the code kind of leaves it up to interpretation and leaves it on you as an engineer to figure out which value to use. I should also mention with the other two methods, FY and when you use the FY method and the FPS method, the only strain you can get is epsilon sub PU because you're not doing strain compatibility, so you don't even calculate the other strains. And so you just go back and you use similar triangles afterwards, just like you do a regular reinforced concrete, and calculate what that epsilon sub PU is. And so that's the only one that exists for the other methods. You don't calculate the other strains for that method. So that's the one there. The other thing it's worth noting is we do lose some conservatism. I don't think you need the is in there, right? Regular reinforced concrete, it goes like this, or regular steel, it goes like that, and then it goes like this, boop, right? And we assume in regular reinforced concrete, we always assume that this is just FY, but really, we assume that it's just FY, but really, this could go up to about 1.5 times FY, and so even though we pretend it's only FY, there's actually some conservatism built into that because our steel will actually be 50% higher. With this stuff, with pre-stressing, that, like we said before, there isn't a well-defined, right? And so we're up in here, right? We're up in there, and we know that we're up in there, and we don't have this 50% reserved capacity floating around, right? Whereas the other method, we have that 50% reserved capacity. It's kind of like it's an inconsistency in the code there, because we do a part of all their calculations does account for the fact that there is some reserved capacity in that material. Regular reinforced concrete has reserved capacity. Regular pre-stressing steel has no reserved capacity. So you may just make the loss of conservatism. I got a V in there. Let's see what Siri says about this. Conservatism. All right, we're good. Not having strain hardening. That's called strain hardening when the thing ramps up. Conservatism. Okay, how are we doing? 2 minutes. All right, we'll leave this for next. So this is what gets a little convoluted too. So on Friday, come ready to get your mind twisted a little bit. This has to do with the minimum amount of steel that you include. And it's very similar to regular reinforced concrete. Well, there's a little prelude to this. Regular reinforced concrete, even if your ultimate capacity is big enough to carry your loads, if your ultimate capacity is less than the cracking moment capacity of your beam, you cannot design it that way. Even if your capacity is greater than your demand, if your capacity is not bigger than the cracking moment, you're not allowed to design it that way. It has to do with failure. If for some reason the loads did exceed the demand, right, exceed the capacity, if your ultimate capacity is less than your cracking capacity, there'd be no warning. The beam would just be like nice and tight, no cracks, and then the load gets big enough, the beam cracks, and then the mechanics switch to this type of mechanics, and it's not strong enough to catch it, and then it fails like in a super brittle fashion. And so there's a limit. And the same thing applies for regular reinforced concrete. It's just now it's applied to pre-stressing, which gets really convoluted. You can run into a case where you're chasing your tail trying to fix the problem. And so there's a simple fix, but we have to make sure that works. The ultimate capacity has to be greater than the cracking capacity, and it has to be greater than the demand. It has to be bigger than both of them. So we'll cover that next time.